Welcome to this session on session 3C on electronic design automation. Myself, I'm Anand Bulusu. I'm a faculty member in the Electronics and Communication Engineering Department of IIT Roorkee. I have been in here for around 13 years now. Before that, I was working in Freescale Semiconductors, and I did my PhD from IIT Bombay. Um, so my area of work is device circuit interaction models, timing models, and for circuits, considering device level phenomena at circuit level abstraction, and the circuits and device physics. So I will introduce I will introduce the authors of the first paper to be presented now. Um, this paper is entitled "Coverage Artifacts for Periodic Signals Using Sequence-Based Abstractions." Coverage articles for periodic signals using sequence-based abstractions. The authors are Ayan Chakrabarti, Sayandeep Sanyal, Vallabh Dasgupta, Aritra Hazra, Scott Morrison, Sudhakar S, and Lakshmanan Balasubramanian. So I'll invite Ayan to present the paper.
Hello everyone, my name is Ayan Chakraborty. Today I will be presenting our work on tracking coverage artifacts for periodic signals using a novel sequence-based abstraction. This work is part of a collaboration between IIT Kharagpur and Texas Instruments and is supported by the Semiconductor Research Corporation. Periodic signals are widespread in MS systems and are essential to their correct functionality. For example, clock signals. Any change in the dynamic of periodic signals, for example, change in frequency or change in DC reference, may indicate anomalous behavior in the systems producing these signals. For example, jitter in the output of a phase lock loop, change in frequency of ripples in a buck converter, frequency drops in power grid signals, and so on. Hence, it becomes imperative to design an automated CAD framework that can track the variation of these properties throughout time. It is also essential to ensure that the tool must be able to work in the absence of any prior information regarding the signal. This should be done to ensure that the tool is generic enough to be applied to a wide range of signals. Now, one trivial way of calculating the frequency is if we already know the DC level value. We can just measure the time difference between zero crossings to get the time period and correspondingly get the frequency. However, this simple method cannot be applied to a wide range of signals and has several drawbacks, which I will explain with the help of this waveform. The first drawback is that the user must know the variation of DC level for the entire signal. In this example, we can see clearly that there are two distinct DC levels, and the user must know both of them in order to calculate the frequency variation using this simple method. Second of all, the expected theoretical value of the DC level that the user expects may not match with the actual DC level that's present in the signal. This mismatch may cause incorrect frequency computations to be carried out if we just use the prior information. One alternative approach to calculate the frequency variation is by using time frequency transforms. For example, the wavelet transform and the short time Fourier transform. However, these time frequency transforms also have several drawbacks. The first drawback is that they do not have sufficient frequency resolution. It is inherently limited by the Heisenberg uncertainty principle. The second drawback is that they are unable to distinguish between transient frequencies and actual periodicity. For example, in this ECG signal, there are several spikes, each occurring at regular intervals, and each spike is made up of a large number of frequency components. Both of these time frequency transforms are able to capture the high number of frequency components making up a single spike, but they are unable to capture the periodicity of these spikes. That is, they are unable to capture the frequency at which these spikes are occurring. This crucial information is missing from both of these transforms. Our algorithm aims to solve this drawback by capturing that essential piece of information, as we can see here. Next, we move on to our proposed methodology. So consider this periodic signal. First, we divide the entire range of the signal into distinct levels. In this example, we have taken 5 different levels A, B, C, D, E, which are 5 distinct values from between point 1 to point 5. An event is defined as crossing of one of these levels by the signal. So the first event is occurring at this point, the second event is occurring here, the third event is occurring here, and so on. Now this entire signal can be encoded as a time sequence of these events. So for this signal, the event of crossing level A occurs first, then B, and so on. So the encoding for the signal will look like this: A, B, C, D, E, and then again E, D, C, B, A, and then it will again continue. We make an important observation that given such a sequence, the shortest subsequence that can be repeated to form the entire subsequence represents one fundamental time period or one cycle. In this example, the subsequence highlighted in red, which is A, B, C, D, E, E, D, C, B, A, we can observe that if this is repeated, this can reconstruct the entire sequence S. And in the signal, this corresponds to this cycle, which and it represents one cycle or the one fundamental time period. So the problem of finding the subsequence from the entire sequence can be reduced to an approximate string matching problem. It is approximate because there may be additional events in the encoding which may be caused due to additional samples at the beginning or at the end, or due to noise. In this example, we can see that there are two additional events due to uh, due to a noise in the signal, which is shown by these two extra literals B and B. So in order to calculate the shortest repeating subsequence, we must be able to tolerate these extra additions due to noise. Now, once we have found the all occurrences of the shortest repeating subsequence, we can then use that information to calculate the frequency. So we just make the observation that the time difference between the starts of two consecutive shortest repeating subsequence gives you one time period. And similarly, the difference between ends of two consecutive shortest repeating subsequence also gives me time period. So for this window, T3 minus T1 is one time period value, T4 minus T2 is one time period value, T5 minus T3 is one time period value, and so on. So the time period that's reported for this entire window is a median of all such values, as you can see here. Once we have found the time period, frequency is simply calculated as the inverse of this calculated time period T. And this computation is done window-wise over the entire signal. So if there are multiple frequencies present in different parts of the signal, our algorithm is able to track those frequencies. Now let's move on to the DC level calculation. So we initially take a window which contains at least 2 cycles, because since we already know the time period from our previous calculations, we can generate this initial window which contains at least 2 cycles. Now and then we resample this window because to take the mean we need to resample it first, because the signal may be adaptively sampled earlier. After resampling, we make an observation that there may be additional samples in the signal, for example at the beginning or at the end, which do not belong to any cycle. And if we directly take the mean, these extra samples may skew the mean away from the actual DC level. So to solve that problem, we first calculate a temporary DC level, which is the mean of all samples inside the initial window. This will be somewhere between the minimum and the maximum. And once we have the temporary DC level, we make the observation that the window between two positive zero crossings of the signal gives me one exact cycle. So this exact window contains just one cycle, and all of the signal points inside this window belong to this cycle. And the mean of all of these points will give me the actual DC value. Peak to peak calculation is relatively straightforward. It is just the difference between the maximum and minimum values inside the exact window. Duty cycle can also be calculated using the previously calculated time period and DC level values. So T on can simply be calculated as the difference between a time difference between a positive zero crossing and the negative zero crossing of the actual DC level by the signal. So that gives me T on, and time period T we have already calculated earlier. So duty cycle can simply be computed as the fraction T on by T. So and in case there are multiple such values reported, we take the median of all values for the window. Now let's move on to results. Here we have the output of a digital control oscillator, and it has square pulses. We we can see that there are multiple changes in frequency and amplitude occurring throughout time. So so there are noticeable changes. For example, at around this point, the frequency changes as we can clearly see, and this is captured by our graphs. However, we can see that at around 14 seconds and at around 86 seconds, there are subtle changes in frequency which cannot be observed by the naked eye. If we zoom in, we can see that there are frequency changes occurring at these points, and these frequency changes have been captured by our algorithm as indicated by the dip in frequency occurring at these points. We can also see that the single cycle fault occurring at around 48 seconds, in which the frequency has decreased for just a single cycle. This is also captured by the sharp dip in frequency at this point. And at around 60 seconds, there is a brownout cycle in which both frequency and amplitude have decreased sharply, and both of these variations have also been captured by our algorithm. Next, we move on to the output of a buck regulator. The output of a buck regulator starts increasing from 0 and finally reaches its steady state value. Now, while it is increasing, it does not increase smoothly. If we zoom in, we can see that there are ripples in the output of the buck regulator. And to calculate the frequency of these ripples is a non-trivial task because their DC reference is continuously changing. However, we see that our algorithm is able to tackle this use case as well, and we get a smooth value of frequency for the entire duration of the ripples. At the end, when it starts saturating, the ripples start dying down, and this is confirmed by the fact that our algorithm also shows that the frequency starts decaying down gradually during the steady state. So our algorithm is able to tackle this use case as well. Next, we move on to the output of a PLL circuit. Now, the frequency of a PLL circuit follows second order characteristics, and that is also confirmed by the result of our algorithm. You can see that the frequency starts from an initial value, and then it follows second order characteristics and initially and finally reaches a steady state value. We also show our results on a ECG waveform, and we can see that our algorithm is able to capture the periodicity of these spikes, that is the frequency at which these spikes are occurring, and this solves a drawback that we had previously discussed. Next, we have two interesting use cases in which there are single cycle faults occurring in a clock waveform. In this example, there is a decrease in duty cycle for one cycle, and in this example, instead of a square pulse, we get a triangular pulse for a single cycle. Both of these pulses have been caught by our algorithm, as you can see by the decrease in DC level and the duty cycle at these points, as well as a sharp change in frequency also. So our algorithm is able to identify these bugs as well. In conclusion, we have proposed novel techniques to track various artifacts of a periodic signal. We perform the computation in the absence of any prior knowledge regarding the supplied signal, and in this way we overcome the drawbacks of the traditional approaches that we had discussed earlier. We have proposed different coverage artifacts for these periodic signals as well as a custom language for specifying these artifacts. We have proposed a novel methodology by abstracting the signal as a time sequence of literals. And finally, we have demonstrated the applicability of our approach over several industrial and other benchmark circuits. Thank you.
Thank you for the presentation. uh, uh, I invite any questions. Are there any questions from the audience? No questions. Okay. So I wanted to understand if suppose there is some periodic signal, say substrate noise or due to some crosstalk or talk, there is a periodic signal interfering with the actual signal. So can your same methodology can be applied to obtain the I mean if you scan at different DC at different levels of voltage, you can obtain the information about that periodic signal also from your method, I guess, in the sense that there are two periodic signals. One is interfering, and so the actual periodic signal you are estimating. You can also estimate the second one,
Yeah,
the
so
other
that
periodic
is
signals.
Yeah, so like that is true. That depends on what time scale we are observing the signal in. So if you zoom in into a part of the signal in which the effects of the secondary frequency is more visible, and then we apply our algorithm there, then it will be able to detect the secondary frequency. And
Okay.
at the upper level, where at like looking at the like at the entire signal, then it will detect the primary frequency of the signal.
Okay. So one thing was if there is such a periodic signal, says because of substrate noise, which is interfering with your signal, would it not change the DC level in the way you are measuring it or obtaining it?
Yes, so like the DC level will be like whatever is actual, like the DC level, and if there is any noise due to cross substrate other signals, then the DC level will be like changed accordingly. But depending on like what frequency we actually capture, like that depends on what is the granularity of the levels that you are taking, and if the if the crosstalk is like not very large enough, we'll get more or less accurate results.
Yeah. Okay, fine. Thank you. So we thank the authors for the nice presentation. Yeah, and let us now move to the second question, second paper, 3C2. It's entitled Avoiding Global Routing for Multiple E-beam Lithography. Its authors are Kritant Saha, Sudipta Paul, Pritha Banerjee, and Susmita Surkolai. So invite the authors to present the paper.
Hello everyone, myself Kritanto Saha from Indian Statistical Institute. On behalf of other authors, today I am going to present our paper titled Stitch Avoiding Global Routing for Multiple E-beam Lithography. This is the topic I will discuss today. As we know that the 193 nanometer emulsion lithography is the most commercially used IC fabrication technique. However, as the time progresses, the feature size decreases, which creates a gap between the lithographic wavelength and modern feature size. It leads to pattern distortion, electrical violation, etc. Several mitigation techniques such as OPC, MP has been proposed. However, they fail to compensate pattern distortion for feature size less than 45 nanometer. The next generation lithography techniques overcome the problem of 193 nanometer emulsion lithography. Our proposed work is for multiple E-beam lithography. In MEBL, thousands or millions of electron beams are used in parallel to write the patterns on the layout. The layout is split into vertical stripes, and the stripe boundaries are called stitch lines. Each stripe is written by different electron beams or in different writing passes. Although this technique has massive parallel exposure, however, the patterns near the stitch line suffers from overlay error because there is a deflection limitation between each adjacent beam. This overlay error causes pattern distortion as shown here. As we can see in this figure, severe pattern distortion occur on vertical segment and via that are routed on the stitch line. The distortion in the horizontal wear is negligible. The region within the distance epsilon on both sides of the stitch line is called the stitch unfriendly region. If a horizontal wear crosses a stitch line with a landing via in the stitch unfriendly region, then that via also face the overlay error. These are called short polygons. Hence, these three violations causes pattern distortion. Here, via and vertical routing violation are considered as hard constraint as they always produce severe pattern distortion. However, the short polygon violation do not always cause severe distortion, hence considered as soft constraint. Hence, the aim is to minimize these three types of violations. Now, in literature, several methods have been proposed to minimize these violations. However, these methods minimizes the violation in the detail routing phase or in the post-routing phase. As we know that the result of detail routing heavily depends on the result of global routing. So in this work, we focus on minimizing the stitch line violation in the global routing phase. Now our method is based on the grid graph model, and we define the cells that contains stitch line as stitch holding cells. We define new routing capacities. If a cell contains a stitch line, then we reduce the routing capacity of that cell. We also define a stitch avoiding vertex capacity to reduce the number of pins or vias on a particular cell to minimize via and short polygon violation. We first classify nets into multi-pin net and two-pin net, and further classify the two-pin net into flat nets and bend nets depending on the position of the pins. Hence, our inputs are the netlist, stitch lines, the grid graph, and our objective is to find a set of stitch avoiding rectilinear paths that satisfies the routing and vertex capacity constraint and also minimizes the wear length and routing bend. Now let us discuss about our proposed method. The figure shows the framework of our proposed stitch avoiding global routing. It is composed of two phases. Our proposed method is inspired by the box routing technique proposed in box router. Now, in the first phase, we first construct a Steiner minimum tree for multi-pin nets. After that, we perform two shifting operations, namely the Steiner branch shifting and Steiner point shifting to minimize the stitch line violation. And this constructs a stitch avoiding Steiner minimum tree. Now, the slide shows an example of our shifting methods. The leftmost figure shows a Steiner minimum tree where a Steiner branch is on the stitch line, causing vertical routing violation and via violation due to the Steiner point and the branch. Hence, we perform SBS to shift the branch out of the stitch unfriendly region as shown in the second figure. Now the tree does not produce any violation due to the Steiner branch. Similarly, in the third figure, we have a Steiner point that causes short polygon violation. Hence, we perform SPS to remove it. However, shifting can increase wear length little bit. Now, in the second phase, we first route the flat net using a shortest path algorithm. Next, we decompose the stitch avoiding Steiner minimum tree into two-pin segments, and we then define the initial position of the box. We use a stitch constraint ILP to route the bend nets and segments present in the current box. The unrouted nets are routed using stitch constraint mesh routing. Then we expand the box to include new nets inside it and route them again. This process continues until the box covers the entire routing region. Now first we decompose the stitch avoiding Steiner minimum tree into two-pin segments and then classify them into two categories as shown in the slide, depending on the position of their endpoints. Now here we categorize the TPBNs and TPSs inside the kth box into three categories. The category 1 and category 2 TPBNs and TPSs inside the kth box are routed by using our stitch constraint ILP. For each category 1 TPBNs and TPSs, we consider two L-shaped candidate patterns as shown in the leftmost figure. As the category 2 TPBNs and TPSs are not routed during the K-1th box, hence they require more bends, and we use two candidate patterns as shown in the rightmost figure. The category 3 TPBNs and TPSs are not routed using the ILP. They are routed using stitch constraint mesh routing as they need more bends. In our stitch constraint ILP, as we can see, different weights are assigned to different candidate paths. The weight function shows that the gamma factor depends on the length and type of net or segment, and the alpha factor depends on the position of endpoints of segment or nets with respect to stitch line, and the last factor depends on the routing congestion. Now the value of alpha depends on the position of endpoints of segments and nets with respect to stitch lines. We have identified three cases. The figure shows an example of case 1. Here, two L-shaped candidate patterns for a particular net are considered in the ILP. The alpha 1 weight is assigned to path x1 and alpha 2 weight is assigned to path x2. Here in the leftmost figure, if we select the candidate path x1, then a short polygon violation occurred at pin P1. As P1 is a fixed pin, we cannot remove this violation anyhow. However, if we select the candidate path x2, then no short polygon will occur at pin P1. However, we need to connect the horizontal and vertical segment of path x2 by a via in the detail routing phase, which can create a short polygon violation during detail routing. We can handle this short polygon in the global routing phase itself. We can introduce a Steiner point outside the stitch unfriendly region as shown in the rightmost figure to eliminate the chance of occurrence of short polygon at the junction. Hence, path x2 is better as compared with path x1. So we assign higher weight to alpha 2 than alpha 1. A higher weight means a higher preference for selecting a particular candidate path over other. Our proposed stitch constraint mesh routing is based on Hadlock algorithm and is used to route the unrouted 2-pin flat nets and the category 3 TPBNs and TPSs in the kth box. In our method, we use these 4 parameters, which includes the stitch penalty and assign a cost to each explored vertex during the exploration phase. We have defined the cost function as shown in the slide. And in the retract phase of our mesh routing, we find the path with minimum total cost. Now let us see some of the results that we have obtained. We run our global router on the Faraday's benchmark circuit. We considered the distance between the two stitch line 15 times the routing pitch, and our global router achieved 100% routability for all these circuits. Here, the result shows that SBS and SPS can significantly reduce the violation due to the Steiner branch and point. As the figure shows, after applying SBS and SPS, we can remove the Steiner branch and Steiner points that are present on the stitch line by 100%. Now, the slide shows that SBS and SPS can also reduce the number of Steiner branch and point in the stitch unfriendly region by 63% and 48% respectively. Although we have applied the shifting technique, a very small increment in the half perimeter wavelength is observed in the result. The slide shows that our proposed global router does not generate any Steiner branch or Steiner point on the stitch line after global routing. Our approach generates no vertex overflow, whereas the box router generates a vertex overflow for RISC2 circuit. Now the wavelength of our proposed method is more or less same as a box router. However, our proposed method takes more time than the existing method. Now, to show the effectiveness of our proposed stitch avoiding global router, we have performed detailed routing. For detailed routing, we have applied regular route. Due to the unavailability of the source code of regular route, we have implemented it by ourselves. As the figure shows that our proposed stitch avoiding global routing followed by regular route can able to reduce via violation by around 17% and short polygon violation around 6%. During detailed routing, we have blocked vertical tracks that are present on the stitch line. Hence, no vertical routing violation occurred for all the three routers. Now, the routability and the CPU runtime is also improved very minimally. I conclude my presentation by summarizing that we have designed an efficient stitch avoiding global router which shows a significant reduction in the stitch line violation counts. A stitch avoiding detail router can further reduce the stitch line violations. Hence, designing an efficient stitch avoiding detail router is the future scope of this work. Thank you.
Thank you for the nice presentation, Kritanta. So any questions from the audience? So I see no questions. I would like to ask, your method involves wherever there is an unfriendly region, then the stitch points or bias are taken outside that unfriendly region, isn't? So can it also lead to without going for another extraction round? Can it can also perhaps very easily lead to an estimation of the increase in capacitance in situ?
Sorry, sir, I am not getting the question.
Yeah. I was just asking. See, your method is based on taking the stitch points or wires outside the unfriendly region.
Yes, sir.
Yeah, so it can perhaps very easily lead to an in situ estimation of the increase in capacitance, wire capacitance.
Yes, but we did not always introduce a new via outside the stitch unfriendly region. Sometimes we select alternate paths. So the number of vias is not increasing, or number of vias on number of stainer point is not increasing for each and every net. It will
Yeah.
for a small portion of net.
So whenever it leads to an increase, you can in situ estimate the increase in capacitance, isn't it? Or such things.
Yes.
So that one need not go for another parasitic
Yes.
extraction round.
Yes, but maximum time we are able to
Why?
get yes, we have able to get additional paths to route the net.
Okay, fine. Thank you. So thank you for the nice presentation. So I would now introduce the next paper, um, 3C3. It is entitled Robust Estimation of FPGA Resources and Performance from Python Level CNN Models. Its authors are Pingaksha Goswami, Masood Shahshahani, and Dinesh Bhatia from University of Texas, Dallas. So I would welcome the authors to present their work.
Hello everyone. Today I am going to present my work on robust estimation of CNN FPGA resources and performance on CNN model. In this work we have created a two-stage post-route QOR estimation tool for CNN architecture using machine learning. The first stage is a global predictor and the second stage is a detailed predictor. Let's first go over the basic architecture of a CNN design. A CNN design consists of multiple variables like number of layers, types of each layer and dimension of each layers. So generally, a CNN architecture consists of three different types of layers: convolution layer, pooling layer, and fully connected layer. So in this diagram, we have shown the image of a linet which is used to detect handwritten digits. So in this slide, I have shown the different variables used in CNN, like number of layers, number of convolution layer, number of pooling layer, and number of fully connected layer. And inside each layer, we have various other finer details like kernel size, stride size, number of input feature map, and number of output feature map. These two sets come from the software definition, like from the Python level. And once we map the CNN architecture into hardware, we have some other variables to take care, which includes pragmas, clock frequency, resource requirement, and latency requirement. So this forms the hardware part of CNN architecture. So let's briefly go over the contribution of this work. The main contribution of this work is a two-stage methodology to predict the post-route QR of CNN design. In the first stage, we created a global predictor in which the machine learning model, it extracts features from the high-level Python code. So these features include the software variables, which like number of layers, number of convolution layer, number of pooling layer, number of FC layer, kernel size, stride size, number of input feature map, and number of output feature map. In the second stage, we use a detailed predictor. So from the first stage, the global predictor will give us some designs which are highly optimized in terms of area, resource requirement, latency, and accuracy. We select very few designs, maybe like 10 or 20 designs from the global predictor, which has very high accuracy and low latency and low area overhead. So those 5 to 10 designs, we map it in the detailed predictor, and we perform design space exploration by changing the pragmas and frequency settings. And then we do prediction using detailed predictor, the post-route QR prediction using detailed predictor. Is in this work, we achieved average mean absolute percentage error of 9% for global predictor and 4% for detailed predictor. This is our FPGA flow. The FPGA flow consists of the FPGA flow. This is our flow from CNN to FPGA. So in the it primarily consists of two parts: the software flow and the hardware flow. The software flow mostly takes place either in GPU or CPU during training, and once the model is trained, we import the number of layers, number of convolution layer, number of pooling layer, FC layers, and then the dimension of each layers. And then we move to the hardware. In the hardware, for inference of the CNN, we define our own CNN architecture based on the dimensions given by the GPU. So we create our convolution layer, pooling layer, FC layer, and fully connected layer. So during the hardware implementation part, we optimize each of the functions. We write the convolution layer, pooling layer, and all those things in HLS or in C++, and then we optimize them area and minimum latency. And once we get the optimized top module, we stitch them together to form the top module. And in the top module, we do some fine tuning of the top module by doing some very minor design space exploration by changing the once the pragmas are once we get the base top and then we map them into FPGA for physical synthesis. This stage consists of mapping, logic synthesis, placement, CNN flow from software definition to FPGA is quite complex. So the limitation of this flow is it has too many steps. Finally, we only want to have only one or very few designs which have low area and low latency and very high accuracy. And then sometimes the designer may have end goal surprises like the timing or the area may not meet. So, and also I have plotted this graph where I have shown you how much time it takes to do C synthesis and logic synthesis in CNN. For a simple architecture containing one convolution layer, one pooling layer, and one fully connected layer, it takes up to 1800 minutes to generate 160 designs for design space exploration. For larger designs consisting of two convolution layer, two pooling layer, and one fully connected layer and consist of 600 design space, it may take up to 7000 minutes, which is very high. But the end goal is to generate only one design. In order to speed up the design process and help the designers, we came up with a machine learning based methodology where the designers do not have to perform any C synthesis or logic synthesis in their designs to generate their post-route QR. They just have to give either the CNN architecture in C++ or Python level to the machine learning based predictor to get the post route QR. That means resource requirement, which includes LUT, block RAM, and DSP, and performance include latency and clock period. So this is our mapping from global predictor to detailed predictor. In global predictor, we do Python level optimization where we change the number of input layer, number of CNN architecture, kernel size, and stride size to minimize the latency and area, and also to improve accuracy. And from the set of designs generated by global predictor, we select some designs, maybe like 10 or 15 designs with very high accuracy and low latency, and map them into the detailed predictor. In detailed predictor, we further fine-tune them by doing design space exploration and changing the pragma settings and clock frequencies. So this is our global predictor framework. So global predictor works in a bottom-up fashion. Initially, we predict the resource requirement and latency for each of the layers of the CNN, means convolution layer, pooling layer, and fully connected layer. And later, if we have two convolution layer or two pooling layer, we predict for each of the layers. And later, for the top module, we add each of the predictions given by the convolution layer, pooling layer, and fully connected layer to get the performance and area requirement of the top module. So in global predictor, the features comes from the CNN architecture, which includes layer size, window size, kernel size, stride size, and number of input-output channels. The output levels are coming from two stages. Either we can take the output levels from the post-C synthesis stage or post-logic synthesis stage. So we run experiment on around 450 designs. 70% of which were used for training, and then 30% were used for testing. We created three different models: gradient boost regression, random forest regression, and multi-layer perceptron based regression model to test the model accuracy. So we achieved accuracy less than 10% for all the three models and for all the 5 predicted parameters. But it has been found that gradient boost regression gives us the best result, where the average accuracy is 8.6% for all the 5 predicted parameters. So after the detailed prediction stage, global prediction stage, we move to our detailed predictor. The global predictor will give us very few designs which we will further optimize using our detailed predictor. So the features for detailed predictor comes from two sources. The first one is the CNN architecture, and the second one is the HLS design. The CNN features are very much similar to the global predictor, which includes kernel types, number of layers, strides, input output, feature map, etc. and from the HLS we convert the HLS into LLVM IR. LLVM is a compiler like GCC which generates a technology independent assembly language code called intermediate representation. We further generate some graphs from the LLVM IR graphs like call graphs, control flow graphs, and data flow graphs. And then we analyze each of the graphs, LLVM IR and HLS code, to generate the features from the high-level synthesis. Later, we combine these two features to our machine learning model. Similar to our detail predictor, similar to our global predictor, in order to generate our labels, we pass each of the design through the physical design flow, and the labels can either be generated after the C synthesis stage, that means the HLS level, or after the logic synthesis stage, the logic synthesis levels. So if we want to do prediction, we just have to convert the high-level code written in Python or C++ into LLVM IR and the corresponding graphs and extract features to generate the post-route QR. We performed 3 experiments in the detail predictor. In experiment 1, we kept the architecture same, means LeNet 5, and also the number of layers fixed, but we varied the internal dimension. That means we varied the kernel size, stride size, number of input feature map, output feature map, etc. In experiment 2, which is similar to design space exploration, we keep the architecture fixed as LeNet 5, and also the number of layers and organization of the layers and the dimension also kept same. In the third experiment, we varied everything, and then we tested on 4 different CNN architecture containing varying number of convolution layer, pooling layer, and fully connected layer. So these are our results from the first experiment, where we kept the architecture fixed but varied the dimension. So as you can see from this particular graph, we achieved less than 8% error for all the 5 predicted parameters. And this graph shows that our predicted parameters are highly correlated with the actual values. Like this is for clock period latency, this is for clock period, and this is for resource. In the second experiment, since we kept both the architecture and the dimension same, and then we only changed pragmas, we changed these 5 pragmas: loop unrolling, loop pipelining, array partitioning, array reshaping, and function instantiation. We get very less error, less than 3% error for all the 5 predicted parameters. For clock period and latency, the error is almost close to 0. In the third experiment, where we trained and tested on multiple CNN architecture, the first table shows the characteristics of training dataset. So we tested on 2 different architectures, which contains 3 convolution layer, 2 pooling layer, and 2 FC layers, and second one consists of 1 convolution layer, 1 pooling layer, and 1 FC layers. Our layer-wise prediction is very less, almost close to 0% for BSP and block RAM, and less than 6% for rest others. For both C3, P2, F2, and C1, P1, and F1. And later, when we map these results to the top module, in the top module also we achieve less than 10% error for all the 4 CNN architectures. So basically, in this work, we proposed a 2-stage design space, 2-stage post-route QR estimation tool for CNN. The first stage is a global predictor which extracts features from the CNN description, and the second stage is a detailed predictor which extracts features from the HLS code, and then we achieve mean absolute percentage error of less than 9% and 4% respectively for global predictor and detailed predictor. Thank you.
Thank you, Pingaksh, for the presentation. So, are there any questions from the audience? Yeah. So, I would like to ask 1 or 2 questions. So, what is the overhead because of the training of your global predictor and the detailed predictor? So how many, I mean, you need to give some design cases for it, isn't? So is there a way to smartly select the design cases, test cases?
Uh, like the training for the CNN or training for the software CNN or training for our model. Our
Yeah,
model does not predict the images. So which training are you asking?
training for your model.
Oh, so in our model, we generated like lot of different CNN architecture, around 6 different CNN architecture, and for each different architecture, like in each for each of the different architecture, in some we, as I have mentioned in the presentation, in some we kept the number of layers and the arrangement of the layer fixed, but in the third experiment we varied everything, the number and the or arrangement of the layer, as well as the kernel size, stripe size, etc. So everything we varied. So for training we created 3 different model. For the first one, we kept each of the layers same, but the stride and kernel size were different. So for that one we took around I think 70% of the design for training and 30% for testing. And those designs where we want to put design space exploration, those comes from the global predictor. And similarly in global predictor also the designs the pragmas are kept fixed, but the rest everything's are varied, like the kernel size, stride size, frequency, etc.
Okay, okay. Thank you.
I think, Anand,
Yeah.
I think the main question that you are asking has to do with however many number of designs were, or what is the overhead of creating the model.
Yeah.
And I think what we ended up doing is, by the time we went from experiment 1 to 2 to 3, because there is so much regularity in the CNN architectures in terms of, in general, the computational structure of convolution is pretty much the same, irrespective of whether you put it in AlexNet or VGG or GoogleNet. The convolution in computation does not change. So as a result, what happened is, by the time we were finished, we actually had a generalized model, which means now we don't need to train anymore. If you want to come up with a new CNN of your choice, you can just run it through my model, which just sits there on the side and is the predictor, which means no more training needed. That was the final conclusion that we had.
Okay, okay. So the model itself is now, so no more training is needed for any new
No.
case. That,
Yes.
thank you. Thank you for the nice presentation and paper. So I'll
Thank you
now,
too.
yeah, thank you. I'll now start the next paper, which is C3, 3C4. It's entitled Identifying Combination of, okay, I have, right. So I'll just read out the title. Identifying combination of defects and unknown defects on semiconductor wafers using deep learning and hierarchical reclustering. So its authors are Ankit Gupta, Adrita Barare Damini, Kirti Kiran Jagannathachar, and Singwok Lee. Singuli Janghun Ho Oh, and Jungha Kim, Minju Kim. So this I will start the paper presentation. Right.
Hello everyone, I'm Damini and I'm honored to present our paper Identifying Combination of Defects and Unknown Defects on Semiconductor Wafers Using Deep Learning and Hierarchical Reclustering. First, I would like to thank my co-authors Ankit Gupta, Adrita Barari, Kirti Kiran Jagannathachar, Sang Woo Lee, Jang Hoon Oh, Junga Kim and Minju Kim for their valuable contribution to the paper. The presentation is organized in the following manner. First, we will start with the introduction to wafer pattern recognition. Then we will discuss the dataset that are used for experiments, followed by the proposed approach, and finally we will look at the experimental results and conclusion. During the manufacturing process of wafers, faults are introduced in wafer at various stages. These faults can be caused due to surface flaws, external flaws, and malfunctioning equipment, which result in decreased yield in the manufacturing line. These faults can be represented as binary wafer bin map patterns, where 0 indicates a good chip and 1 indicates a faulty chip. Wafer bin map is represented in binary image data format, where these faults can have some visible shapes and patterns. Some sample defect patterns can be seen in these figures. These patterns are not random, as they have multiple occurrences during manufacturing. Hence, it can be concluded that each of these defect patterns on wafer bin maps are the result of a particular set of flaws. Identification of the root cause of these fault occurrences during wafer manufacturing helps to map a particular defect pattern with a particular cause and can help to further improve the fabrication conditions and increase the yield of the manufacturing line. We used two proprietary production line datasets for developing and evaluating our proposed approach. The first dataset D1 contains 5,000 plus data points consisting of 10 labeled non-defects. The labeled categories in dataset D1 are center, edge, eye, near full, normal, scratch, left side, upside, downside, and right side. Sample images from each of these classes are shown in the figure. And the second dataset D2 that we use contains 6,689 images that are uncategorized. Moving on to the overview of the proposed approach. First, we trained an initial model on training dataset having 10 non-defects that classifies each wafer bin map in 1 out of 10 defects. In reality, though, there may be a combination of defects or no known defects present on the wafer. To address this, multiple high-accuracy 1 versus rest classifiers are trained to identify known defects that occur as single defect or as a combination of known defects on the wafer. However, identification of defect patterns is an ongoing and iterative process. Therefore, previously unseen fault patterns may be introduced because of some new aberration in the manufacturing system. Hence, to identify these unseen patterns, unsupervised clustering techniques with hierarchical reclustering is used. Our initial aim was to classify the wafer bin map within 10 non-defect classes using dataset T1. In order to do this, an ensemble of 3 custom CNN models are trained. We used Inception V3 architecture for model 1 with dropout of 0.4 and an improved custom Inception V3 architecture for model 2 and 3 with dropout of 0.3 and 0.4. Ensemble weights of 1.91, 1.92, and 1.13 are used, which are derived through grid search method. Balanced accuracy of 96.4% is achieved through this approach. Although the ensemble model shows good results for classifying 10 known defects, it lacks in identifying combination of defects and unknown defects that may be present on the wafer. So, our proposed approach overcomes this issue in 2 major stages. In the first stage of our approach, D1 dataset is used to train 10 1 versus rest models to identify single defects and combination of defects. 10 datasets are created by dividing the entire dataset into 2 categories, with and without including each defect. All the defect classes, their corresponding CNN architectures and hyperparameters are tabulated in table 1. With this approach, we were able to achieve an overall balanced accuracy of 95.85%. In order to discover unknown defect patterns, in the second stage, clustering is performed on those samples from dataset D2 for which 1 versus rest models predicted to have no known defects. For selection of most suitable value for clusters K, a combination of mathematical cluster evaluation matrix and qualitative analysis is used. Qualitative analysis includes analyzing the Silhouette plots as well as visually representing the data points in terms of first and second principal components using principal component analysis. As it can be seen in the Silhouette plots that for our data set, although k equals to 2 has a higher average Silhouette score than the average Silhouette score of k equals to 3, but we can see in the PCA plot that the points are emerging from a particular area. So for k equals to 2, the points near that area are considered in one cluster. This is shown in green color, and rest of them are assigned to the other cluster, which is shown in black color. We also confirmed this by random sampling of data points from the clusters to see their visual similarities. So we choose immediate higher value of k, 3 and 4 for clustering. We used two clustering techniques for generating the clusters, k-means clustering and agglomerative hierarchical clustering, and evaluated them based on various evaluation matrices such as Silhouette score, Davies index, and Kalinske-Harabash score. Comparison of these clustering algorithms for k equals to 3 and k equals to 4 is shown in table 2. After all the experiment and analysis, k-means with k equals to 3 proves to be the most efficient as it gives high Silhouette and Kalinske-Harabash score, whereas low Davies index. So k-means with k equals to 3 is selected for all future analysis. Why reclustering is required? Although a thorough mathematical and visual inspection is done to get the value of k, there may still exist certain clusters whose samples do not visually appear similar to each other. So, to make our clusters more homogeneous, we leverage the power of human-in-the-loop concept and perform reclustering of certain clusters wherever required. The flow of hierarchical clustering approach is shown in the flowchart. The decision to conduct reclustering of a particular cluster is taken iteratively by assessing the quality of cluster through the techniques mentioned earlier, and we also sample a small number of data points from the detected clusters for human validation. If the samples are found to be visually dissimilar to each other, reclustering is performed with a suitable number of clusters. This process is repeated until an acceptable homogeneity of cluster is achieved. Moving on to the results. For stage 1, the trained 1 versus rest models are used to label the dataset of uncategorized patterns T2. The distribution of a number of defects for dataset D2 is shown in table 3, where 993 samples found to have no known defects, 4,158 samples had one known defect, 1,363 samples had two known defects, and so on. Few combinations of defects that are uncovered using this strategy are center scratch, and edge right side, which are shown in these figures. Since 993 samples are found to have no known defect patterns, so they are passed to the next stage for clustering. On performing clustering on 993 images, 3 clusters are generated with 61 images in cluster 0, 914 images in cluster 1, and 18 images in cluster 2. Upon qualitative evaluation of D2, cluster 2, shown in yellow color in the Silhouette plot, is found to have 18 homogeneous samples, and thus it is kept as it is. However, for cluster 0, shown in gray color, and cluster 1, shown in blue color, it can be seen that reclustering can reveal better patterns. So, reclustering is performed on these two clusters. While reclustering for cluster 0, k equals to 7, and for cluster 1, k equals to 20 gives the distinct patterns and a positive Celote score for almost all subclusters, as shown in these figures in the right side. So reclustering is performed with these values of k, and after reclustering of these two clusters, 28 new defect patterns are identified from 993 images. These are some of the newly identified defect patterns. Each row in this figure is showing previously unseen patterns which are obtained after passing through 2 stages of the proposed approach. In conclusion, the proposed approach achieves an overall balanced accuracy of 95.85% on dataset D1, and on dataset D2, it identifies 1,538 samples having combination of defects. It also uncovers 28 previously unidentified defect patterns on dataset D2. Identifying defect patterns in wafer bin map helps manufacturing line corner out the stages of fabrication where wafers may develop defects. Consequently, it helps in improving fabrication conditions, rectifying process flows, and increasing the overall yield in the manufacturing line. Thank you. That's it from my side.
Yeah. Thank you for the nice presentation. So, any questions from the audience? Okay. So, there are no questions from the audience. So it is. So you are able to identify new defect patterns with your method. That's so. Um, how many? What is the sample size for training that is required of in this?
Yeah, so for training the CNN, our first model, to classify the known defects, we used 5,000 plus samples overall, and we divided them into a train set and test set.
5.
Yeah,
Okay.
in 20 and 80 ratio.
Okay. So okay. Thank you. So there is a question from the audience, so I'll read it out. What is typically accepted threshold or tolerance values for Davis score below which we accept the model in deployment commercially for this problem? So what is that threshold for deployment?
Okay, so for Davis score, we didn't mention any specific threshold to accept or reject the model. We just used it to compare our results. So there is no specific threshold is used, but as of Davis index, if it is if it has the lower value, then it seems to have the better clustering results. Yeah.
Okay, thank you. Then we move on to the next presentation. So the next paper is 3C5, and it's entitled An Architectural Support for Digital Microfluidic Based Hotspot Free Computing. Its author is Sumanta Paine from National Institute of Technology, Rourkela. So I welcome the author to present the paper.
Hello audience, this is Sumanta Paine from the Department of Computer Science and Engineering, National Institute of Technology, Rourkela. I'll be presenting my work titled An Architectural Support for Digital Microfluidic Based Hotspot Free Computing. This is the overview of my talk. We will see what has motivated this work. The liquid-based cooling of IC in modern times we discussed. We will have a discussion on electroweighting and digital microfluidics, and so how digital microfluidics can be used for designing and architectural support for cooling purpose. As we have seen in past decades, the sizes of the IC have decreased in the sub-micron era, deep sub-micron era, with high speed of operation and the increase in interconnect resistance and packaging density. So the power per unit area, the chip is high, the power density is high, which is leading to overheating of the chips, which may cause chip failure or permanent damage of the chip. This has also increased the reverse saturation current due to rise in temperature. We know that the leakage power increases with the increase in reverse saturation. The interconnect delay increases with rising temperature, which also degrades performance. The existing cooling techniques are mainly based on the fan-based air cooling and continuous flow liquid microfluidic cooling. But these techniques actually lack reconfigurability because they are not able to, since they are implemented in the design time, chip design time, so they are not able to remove large amount of heat from the IC. So liquid droplet phase cooling is a good candidate for the reconfigurable cooling. The first one, which was done in 2000, so where the droplets were evaporated to cool the heated surface of the microelectronic packages. And soon after this work was published, so another some works were done in reconfigurable active cooling using digital microfluidics, where the droplets were attracted, the coolant droplets are attracted at the hot areas by the method of thermocapillarity and effect, and the droplets, after absorbing heat, move to the reservoir by electroweighting. But for this method, actually we have to heat the surface of the processor or the IC at a particular temperature for that to attract the hot droplets. As the temperature increases, the speed of the droplet attracting the hot areas increases. Apart from this, in last decade, the microfluidic cooling has been done using liquid continuous flow liquid microchannels, which are implanted within the chip substrate during the design time. So another more effective cooling can take place. You can do a float planning combined with the liquid micro channel placement. So these are efficient for the 3D cooling and 3D packaging processors and ICs, but still the reconfigurability is not guaranteed. So the electroweighting and is a technique where we can move droplets, liquid droplets, on electrode grids by the influence of voltages. So this has been used to design the digital microfluidic biochip, where we can realize a biochemical lab within a chip. So we can do biochemical reactions for various detection of diseases. Then we can go for all the medical diagnosis test, which we go for blood test, then saliva test, or many medical applications we can done in a very small scale and can save a lot of time and resource as well as money. So this electroweighting based digital microfluidics can be applied to chip cooling. So here we consider a processor flow plan which has been partitioned into 4 grids, which covers the entire floor plan, where the droplets move from the source electrode to the sink source reservoir to the sink reservoir using the electroweighting. So the target regions, the hotspot regions are identified from the control and the signals in the control and the address line of the processor. So this helps in prior detection and of the hotspot formation, and so that the action can be taken, so we can prevent the hotspot before they are formed. So this is an example. You can see that this is a small 4x4 grid which is addressed, the electrode of electrodes which are addressed, and it is beneath the iCache, and from each electrode. So we can, from the if we have a mapping of this electrode positions with the positions different part of the blocks of the cache, then from the address signals we can make out which grid has which part of the grid requires the droplet coolant droplet to flow. So in this way we can use this in the entire processor flow plan to move the droplets to the target regions. So we have implemented 3 instructions have been incorporated with this. So the enter instruction entry, which helps us to enter the droplet in the from the reservoir to the grid, in the grid. So it is by maintaining the fluidic constant, where we have to maintain at least one grid space between the 2 consecutive droplets. So this is an entry. So after the entry takes place, it will move horizontally towards the target position using the move H instruction, where the droplet can move horizontally, and after it reaches the target region, then it can move vertically using the move V instruction. So all the conditions before the checked using the fluidic constraints are checked, so that there is no mixing of 2 different droplets, which can lead to the failure of the cooling. So this is the control unit of this the financial machine, representing the control unit of these 3 instructions, and this is the conditions. We check the conditions and we multiplex the electrode lines, so that we can use only one circuit for each grid. We can have this collection of this one collection of these circuits, so that we can have less amount of hardware requirement. So this is for each different category of electrodes, the sink electrodes, the source electrodes, the entry electrodes, interior and exit electrodes. So these electrodes are actually controlled by these logics which are there, on the basis of which we switch on and switch off these flip-flops, and the droplets can move. The coolant droplet routing uses there's a queue for it. This algorithm runs is run by the thermal management unit of the processor, where each grid has 4 queues. Each grid has a queue where the target position is the hotspot position coordinate, and is stored for each request, as well as the current position of the droplet is also stored. Okay, so when for each horizontal and vertical movement of the droplet, the queue entry for that particular droplet is updated. So here you can see that the droplet, 2 droplets come into for 2 different hotspots, and one after another they go to the hotspot and cool that region, and they exit to these droplets exit to the sink, and the data structures are updated. So the experiments have been carried through simulation. So we have simulated the ARM Cortex A75 core for performance values, and this performance values are utilized to get the power trace from MACPAC, and the power trace and the probe plan of the processor is utilized to get the thermal temperatures for the given power values of different processor units. The four DMF grids have been the simulation environment for 4 DMF grids have been implemented. Each grid is having 16 cross 16 electrodes, and where each droplet is of 1 microliter and can cool has a cooling ability of 5.25 to 12.46 degrees Celsius with droplet speed up to 4 milliliter per minute in each grid. So the maximum flow over all grids can be up to 12 milliliter per minute. The droplet transmitting power from one electrode to another is less than 1 microwatt. So each queue in the each grid has 1024 entries. So the 8 benchmark programs have been considered belonging to the MI and the media branch, and the MACPAD, the GM5 MACPAD and HubSpot combined together to find out the performance values, power traces, the thermal values, and the cooling activity, a module which has been added to the hotspot that uses the droplet movements to do the cooling activity. So this work has been compared with the fan-based air cooling and liquid microfluid, liquid continuous flow, liquid microchannel cooling with 2 channels and 4 channels. So the microchannels, you have the continuous flow, and the flow takes place with the help of each channel has an induction type electrohydrodynamic microform in each liquid microchannel. So you can see the reduction of we analyze the regional peak temperature reduction for each region. See, there is a regional multifluidic based cooling achieves some sufficient amount of heat reduction from the other techniques, and this reflects in the average temperature processor as well as the normalized leakage power is reduced. The cooling power, the overhead of this lies between is just bit more than the power overhead of fan-based cooling, whereas for the liquid microchannel cooling, as we have the more number of channels due to the increase of number of pumps, it requires more area and power. So you can see here with respect to the fan-based cooling, the liquid and the digital microfluidic cooling requires 14% extra space, while the others, the LMC2 and LMC4 requires 12 and 25% each. So this is a summary where you can see that the average reduction of DMF is 26.5%, the average processor temperature reduction, and the leakage power reduction achieved by the DMF is 30.25, which is much more than the LMC2 and LMC4 with respect to the fan-based cooling, but they need some overhead of area and power. We conclude here. We have shown that how four droplet control electrodes can be incorporated in the substrate of a processor, where we can move the droplets, coolant droplets, to the hotspots, which are realized from the control and the address line signals, and the coolant droplets can move horizontally to the hotspots and absorb the heat and move vertically to the sink reservoirs, thus cooling the system, and actually is better cooling than the fan and liquid microchip cooling, but the droplet routing is slow because one droplet moves at a time in each grid. So we need to speed up the droplet routing process for better cooling. Thank you.
Thank you for the presentation. So are there any questions from the audience? Okay, so I have a few questions. So the identification of hotspots you are doing from the address and the control lines. So that's what you're saying. So how is it done, in the sense that are there any temperature sensors, or is it through the change in circuit performance? What is the way?
So actually, when we are doing any memory read or memory write or any ALU operations, so the control signals, actually we are trying to identify the control signals. Okay, so from the control signals and address signals, we are going from the levels, the control in the levels of means the 0, 1 level in the control and address lines. From there we are identifying.
How are you identifying from the levels?
Yes, actually those logic circuits which are there, actually I have shown you that those are actually connected. So we're trying to identify using those logic, and those from there actually we are actually the architectural support I've shown actually in the slide number 10, I think actually there it has been shown. So from there we're trying to identify there's a mapping between the control lines and the address lines with the grid positions. Okay, so when I'm getting that, so from there that mapping is taking place, and in this way
Yeah.
actually
Yeah, I understand. So I was just trying to understand the basic principle. So are you identifying activity, and based on
activity on the
yeah,
basis of the
it
activity.
is, wherever the activity is more, you are
Yes,
yeah.
yes.
What is the impact of keeping one block free? I mean, you can have you cannot have droplets in the adjacent blocks, isn't it? So what is the impact of that on this kind of an
Actually,
approach?
in detail myofluidics, actually, what happens if two droplets are in consecutive grids? Actually, there are chances of mixing. So actually, we maintain a fluidic constant. Actually, this is the design principle actually which is followed. So
No, no,
actually,
yeah, true. Okay, okay. So, um, so here since there are no more questions, so we end the session 3C here. And I'm thankful to Sumanta for presenting the paper.